Hello all. This is Ubad Qureshi, and I'm going to present our paper titled Smart EV Battery Scheduling in a Virtual Power Plant, a Stochastic Receding Horizon Convex Optimization Approach. I'll be going through the following contents: Introduction, Contribution, Model, Problem Formulation, Simulation, and finally conclusions. We know, unlike conventional generators, where the generation can be efficiently and more accurately predicted, intermittent generators cannot engage in electricity market because of their otherwise nature. In order to solve the problem of intermittency of distributed generators so that they can engage in electricity market, one of the ways of solving the problem would have been to use battery storage. Battery storage would have helped to schedule the energy supply to the grid. But the problem is it will require uneconomical investments. We thus propose to store the EV, to store the energy in electric vehicles while incentivizing them with energy credits. However, again, the stochasticity in wind energy generation, changing EV storage availability, and varying market price are critical concerns of a virtual power plant operator. Virtual power plant is basically an aggregation of schedulable loads, renewable energy generators, and maybe diesel generators as well. In this paper, we present the virtual power plants of renewable energy generators and electric vehicles considering the uncertainties so that they can supply electricity on demand, addressing intermittency, and participate in electricity markets profitably. The contributions of our work are: we first formulate the complete optimization problem of scheduling energy to the grid eh, as a receding horizon convex optimization problem with linear constraints that give an optimal schedule even with uncertainties involved. Next, we explicitly model the uncertainties in renewable energy, EV storage availability, and electricity costs. Furthermore, we introduce the novel scheme of energy credits to compensate EV owners whose batteries we are using to supply, to store the distributed energy generated by distributed generators. Finally, we show how our optimization algorithm develops an optimal scheduling policy for profitable power exchange using vehicle to grid and grid to vehicle modes and the novel convex optimization technique using receding horizon control. So first, we'll explain the model of a virtual power plant. We formally let the estimated electricity generated by the virtual power plant, that is distributed generators, on the next day at each time slot be Zn. This estimated quantity can be supplied directly to the grid, or it may be stored in the battery of electric vehicles, or we can do both. Furthermore, for the same time slot, the VPP leader may want to transfer to the grid an additional quantity of electricity that was stored in the battery of vehicles in the previous time steps. These decisions depend on the market price and also on the cost of using the storage. Since we want to maximize the profit of a virtual power plant, so what we basically aim, we want to supply the energy to the grid at those times at which the price of energy, at which the price of electricity is high, so as to maximize our profit. Next is the storage payment scheme. Since we are using the battery of electric vehicle owners to store the electrical energy generated by distributed generators so that we can supply the energy to the grid at profitable times. Since we are using the battery of EV owners, we will have to compensate them. So the payment for storage is provided to electric vehicles not in the form of money but in the form of charging entitlements, what we call as energy credits, rather than the money. This way of paying for storage will help in overcoming the main perceived disadvantage of using EV storage for electricity spot markets, low revenue from the markets, and high cost of battery life. The amount of energy given away is measured as a proportion of amount of used storage. So for example, if we store, let us suppose if we store 10 units of energy in the battery, we may give the EV owner 10% of the energy as energy credits. We'll take only 9 back from his vehicle. So he earns 1 unit for letting us store 10 units in his battery, which thereby acts as representative of the storage cost. Fine. The optimization problem. This is the optimization problem that we are solving in this paper. This optimization paper is being solved by the virtual power plant leader, where Px of D, where P is the profit that the virtual power plant is making. PE of n is the price of electricity at different instants of time. Xn is the array which represents the amount of energy that we are pumping into the grid directly from the renewable generators at each instant of time. D of n is the amount of energy that we are supplying to the grid and draining from the battery of electric vehicles. That is the total energy that we are pumping into the grid is X of n and D of n. The summation of the two is the total energy that we are supplying into the grid. And multiplying this energy by the price at different instants of time will give us the revenue of virtual power plant, which it wants to maximize actually. Next are the number of constraints that are there on the virtual power plant. These constraints are on the total energy generated. These constraints are on the battery capacity, how much energy we can drain from the battery. And similarly, the other constraints are on a different other parameters of the virtual power plant. Finally, when we solve this optimization problem, this is a convex optimization problem, and we solve this convex optimization problem using CVX. We get the day ahead bid W, where W is the summation of X plus D, how much energy to supply to the grid directly from the renewable generators and how much energy should be drained from the battery and supply to the grid. Fine. These are our simulation results. Since we are taking the wind energy here, we could have easily taken in place of wind the solar photovoltaic. We can replace it with solar photovoltaic without having any negative impact on the algorithm. We are treating it like, for example, we have a wind as distributed generation, and this is the wind forecast data, wind power available at different intervals for 96 intervals of time in the day ahead case. Fine. And this is the variation with the sigma, where sigma is the percentage, where sigma is the percentage of the charging entitlements that you give the EV owners, or storage cost percentage and the revenue generated. And next, this is the electric vehicle cost and profit analysis. The more the depth of the discharge, the more the profit the EV owners will make. Fine. The red one shows profit to the EV, and the blue one shows cost to the EV. This analysis is basically, we have performed this analysis actually on basically if the EV owner is letting the virtual power plant leader to use the vehicle, to use the battery of the EV, their battery will get degenerated, or their battery will have some degradation. The degradation cost and the profit they can make. The degradation cost in the blue, they are less, and the profit to EV, they are more. That is the energy credits that EV owners are getting. They are more than the cost they will incur for allowing their batteries for storing the energy. That means they are earning in this case. And finally, the conclusion. The focus of this work was to enable wind power generators to participate fully in electricity markets by forming virtual power plant with EVs that can store the energy to overcome the intermittent nature of energy supply. It showed how the virtual power plants can maximize its profit by optimizing the supply schedule to the grid based on energy production and available storage. A novel scheme of paying EV for this storage but supplying energy at no cost, what we call as energy credits, was introduced. And finally, we used receding horizon convex optimization, and we showed it to be simple and computationally cheap, since at each time step a linear optimization problem needs to be solved. I thank you for your patience. Please, if you have any questions, you can ask me.